We're on right on the 1700, so welcome everybody to our meeting. I'll just meet everybody else. Excuse me while I do this. On behalf of the Federation of Astronomical Societies, I'd like to welcome you to our webinar tonight. Pleased to introduce Alan Stern from the New Horizons exploration of Pluto mission, and we'll come to that in a minute. So thank you everybody for signing up to this meeting. It's nice to see so many FAS member societies people on here, but also I noticed there are some visitors tonight that don't show as FAS member society members. If you want to join the Federation of Astronomical Societies, you need to find your local society that is an FAS member. Once you become a member of that particular society, you will automatically be affiliated to the Federation of Astronomical Societies. My name is Michael Bryce. I am actually the newsletter editor for the FAS, which comes out every 2 months. And we always like to see what societies are getting up to, outreach and that sort of thing, and any observation nights they do, and that sort of thing, and their actual society program as well. So yeah, check out your local society. We have nearly 200 societies in the UK that are members of the FAS, so there should be one near you. So I'd like to pass you over to Jenny now to say a few words.
Thank you, Michael. Welcome, everyone. So glad you could join us today for what is the second of two special events that we've arranged regarding the exploration of Pluto. And the reason for organizing these is that this year marks the 10th anniversary of the New Horizons flyby, and that came about as the result of a proposal by a team in which Alan Stern was involved back in 1989. The mission actually was launched in 2006 and took 9.5 years to reach its first encounter. And I say first because Alan, I'm sure, will tell us about what happened afterwards. Alan is going first because he has a schedule, which means he will have to leave here at 6 o'clock our time. So while he's talking, if he wants to put any questions they have into the chat, please, we'll see what we can do about presenting them to him afterwards. So we are extremely delighted and privileged indeed to have the head of the New Horizons mission. So over to Alan.
Thank you, Jerry. Can you hear me fine?
Yes, we can.
Yes, we can.
Hi, everybody. It's great to speak to you this afternoon. I'm going to tell you a good bit about the New Horizons mission, how it came to be, what it's all about, a little bit about what the findings were at Pluto. I'm not going to say much about the mission since Pluto, but happy to answer questions within the time we have. So I'm going to share my slides, and as soon as we make sure that that's up for you, I'll dive right in. Can you see the slides?
Yes.
All right.
And that's at full screen.
Good. Good. All right. Well, I'm here to tell you about the mission of New Horizons, which I've been involved in even before there was a New Horizons. The group which I was a part of, that began agitating for the exploration of Pluto and eventually the Kuiper Belt, began, as you heard from Jerry, in the late 1980s. New Horizons was invented in 2000 and 2001 and selected by NASA to be the mission to go do that exploration of the ninth planet. And it is the farthest exploration of worlds in history, having gone farther, considerably farther than the Voyagers have gone. And I'll have more to say about that as well. And really interested in your questions when we get to the end. Here on this first slide, to the right of that doorway to the other red planet, Pluto, you see our mission emblem and the primary partners, my institution, the Southwest Research Institute, NASA, and the Johns Hopkins University Applied Physics Laboratory. You may notice that the mission emblem has 9 sides to it for the ninth planet. And to the right of that is a picture of a full-scale mock-up of the New Horizons spacecraft that hangs in the National Air and Space Museum of the United States in Washington, D.C. It's one of only a handful of planetary spacecraft that have ever been invited to have a model at the Air and Space Museum. We're very proud of that. This is really a historic journey all the way. It sounds like science fiction, but it's not. You know, it's a mission all the way across the solar system to the very frontier of human knowledge. As I said, to the farthest worlds that have ever been explored in this third zone of the solar system called the Kuiper Belt. Here is a depiction, a very simplified cartoon depiction of the geography of our solar system. On this scale, the orbits of the terrestrial planets like the Earth and Mars are not even visible. The orbits of the giant planets, Jupiter, Saturn, Uranus, and Neptune, are shown as white ovals. Pluto's orbit is in yellow, and the red line that ends in an arrowhead is the trajectory of the New Horizons spacecraft, which, as you already know, was launched in 2006, flew past Jupiter in 2007 for gravity assist, intercepted the Pluto system in 2015, and is now out exploring the Kuiper Belt and will continue to do so for another several years at least. A little about myself. This is myself with my first scientific instrument, and the only one I think that ever looked anything other than upward. Ever since I was a little kid, I wanted to grow up and be involved in space exploration. I wanted to be a scientist or an engineer, and I was very fortunate that I've had a chance to do that all my life, and be involved now in 30 space missions, mostly NASA, but some ESA missions as well. I've been principal investigator, which means project leader, 15 of these missions, of which New Horizons is probably best known. I work in an office building like most scientists do. I work for the Southwest Research Institute, which is a large nonprofit. We do about $1 billion a year in contract research for government agencies and private industry. This building is our office in Boulder, Colorado, where I live. The actual institute, which has 3,000 employees on our main campus, is in Texas. And I started our Colorado operation. We started with myself and a postdoc, and we now have 120 people in Boulder, where I am. But you know, as I work in office, a lot of the time I'm working on a computer, working on scientific research papers and space missions. I travel a lot in my work. Some of that travel's been rather unusual. I did an expedition to the South Pole to do astronomy down there in the late 1990s. Really a spectacular environment. I spent 5 years flying high-performance jets for NASA in the 1990s and early 2000s to do high-altitude airborne astronomy. These are pictures of myself on some of those missions. I've also been very fortunate to be involved in an expedition down to the Titanic. These are actual home movies that were made with my iPhone in 2022, 14,000 feet beneath the North Atlantic. And in 2023, I flew to space on Virgin Galactic. I'm going again next year. It's an absolutely spectacular experience. I went as a researcher, not a space tourist. and we'll be flying a NASA experiment this time next year, if things go well, on my second space flight. So really looking forward to that. Hopefully more after that. But most of my career has been spent in the pursuit of the exploration of the solar system using spacecraft, not telescopes, although I did a little of that. Spacecraft like this one, this is actually New Horizons, shortly before it was launched, and myself in a clean room where we were assembling the spacecraft. I thought I'd give a little bit of background for those who may not know. First of all, this blurry picture is the best image of Pluto ever made before New Horizons. And it ain't much. Actually, I was the principal investigator of this program that used the Hubble Space Telescope to image Pluto. And it's the first resolved image of Pluto, where you can actually see details on the surface. Not much, of course. You can tell that the North Pole is brighter than the South Pole. And there are some other details that we wrote about in scientific papers. But at this kind of resolution, you really can't do very much science. And that's why we go to the planets, is because really, in order to study planets, you need resolution like this. This is a picture of the Earth made by Apollo astronauts in 1972. And from a single image like this, you can learn a great deal about a planet. Of course, the exploration of Pluto delivered thousands of images and hundreds of thousands of spectra to determine composition and temperature and other properties of the surface, and other kinds of data as well, thermal data, atmospheric data, and so forth, that I'll touch on in this presentation. But my point is that our telescopes, even our best telescopes like the Hubble and the James Webb, are not good enough to resolve the details of faraway places like Pluto. This was true even of Mars and Venus and the inner planets in the early days of space exploration. So we send our spacecraft to get up close so that we can examine these targets in detail. I will drive this point home a little further by showing this blurry image. This is actually the same image of the Earth that you just saw, degraded, repixelated to the resolution of the Hubble image of Pluto. And I'm sure you can agree with me that from this image, you would learn very little about the Earth. It would be virtually impossible to say very much meaningful. In fact, I created this image at the same resolution, and I'll leave it as an exercise to each of you to guess what we're looking at. And some of you might guess Mars, some people guess the sun, some people guess all kinds of things, and none of them are ever right, because what we're looking at is the US American flag at that resolution. And so I'm just driving the point home. We go to the planets so that we can get close enough to really see them in detail. And that's why we flew this mission to Pluto, a completely new type of planet, what we call an ice dwarf in the distant outer solar system. The ice dwarfs outnumber all the other planets combined. The first was discovered in 1930. That's Pluto itself. It took 2 generations for our technology to get better, to be able to see other small planets in the Kuiper Belt. But now we know of many of them, and we expect to find many, many more. And in the 21st century, we're just going to have to get used to the fact that there are more planets than anyone will care to memorize the names of. That our solar system is very good at making small planets, better at it than making bigger planets. And that there are many more to explore. And I hope that we see that exploration in coming years. Now, the exploration of Pluto took a long time to get funded. I was involved in all of the attempts to get a mission to Pluto following the mission of Voyager that ended at Neptune. And we started in 1990 with the first NASA study. It went nowhere. There wasn't enough money for it. In 1991, we tried something else. That also went nowhere, never got off the drawing board. In 1991, we started yet a third study, again funded by NASA, which also never got off the drawing board. And some of these were just mismanaged, and some of these were too expensive, and some of these the time wasn't right, or the budget conditions weren't right. This went on and on and on. And I can tell you that the people who were behind it, myself and many others, had a very strong case. And in the way that we rank missions in the United States, The exploration of Pluto always ranked highly. It would make the A list, but in order to compete in a very difficult funding environment, you really have to be at the top of the A list. And it was only with the first planetary decadal survey where the entire scientific community in the United States agrees to a set of priorities, in which, in fact, the exploration of Pluto in the Kuiper Belt was ranked number one in the early 2000s. That this mission did get funded. And then Congress and the United States president at the time supported that decadal survey. And as a result, NASA conducted a competition. And I was asked to lead two of the teams. I selected the Johns Hopkins Applied Physics Laboratory as the team that I wanted to lead, but it was the underdog team. And very much so. Our primary competition were the incumbents in outer planet exploration, and really in all planetary exploration, the Jet Propulsion Laboratory of Caltech. It was a very tough competition because we had much less experience, but we had a much better proposal, a much better concept for the spacecraft, a much better management team, and frankly, a better scientific payload. And NASA's review of the proposals, and this is the cover of the New Horizons proposal back in the year 2001. This proposal, by the way, it's about this thick, about 1,000 pages of very detailed plans and designs, trajectory designs, spacecraft designs, cost and management volumes, of a lot of science and a lot of demonstration of how this spacecraft and its 7 scientific instruments could revolutionize our knowledge of Pluto and the Kuiper Belt. This 1,000-page proposal got higher ranks than any of the others in that group of 5 proposals that were submitted. And we were selected even over the Jet Propulsion Lab, despite the fact that we were underdogs. And then for the following 4 years, I sometimes call that period the blur from 2002 to 2005, when my team, which consisted of 2,500 men and women working for the spacecraft team at the Applied Physics Lab, at Southwest Research, where we built the scientific instruments and managed the scientific payload, at Lockheed Martin and Boeing when the launch vehicle was built, with the U.S. National Labs that provided the nuclear power supply, and many universities and small contractors around the country. We were given a real challenge when we were selected. First, the budget that NASA assigned to this mission was very precisely 20% of the budget that Voyager had. So we were very highly challenged to invent a new way to do this much less expensively. And at the same time, most spacecraft in the 80s and 90s took a decade to develop for planetary exploration. When we were selected, in fact, in November of 2001 as NASA's choice, we had only 4 years and 2 months to get it built and launched because we needed a Jupiter gravity assist. And the last Jupiter gravity assist of the 2000s was coming in January of 2006. We had to make that launch window. So I call it the blur because all of us signed up to 52 weeks a year and 7 days a week. And it was a marathon. It really was extremely challenging on families, on careers. But we had a team that was very dedicated and that pulled this off on budget at this much lower revolutionary budget and in the short amount of time that was available, and got this spacecraft to the launch pad. Here is New Horizons. In the upper right, in an inset, you can see the names of the 7 scientific instruments, but the main picture shows you the spacecraft in a clean room in Florida shortly before launch. You can see the dish antenna on top that we used to communicate with the Earth. You can see a black cylindrical device on the left. Looks a little bit like a lady's hair curler. It's actually a nuclear battery fueled by plutonium, the element in the periodic table named for the planet Pluto. And we use the radioactive decay of that plutonium to generate DC electricity to power the spacecraft. When the fuel was fresh, it generated 250 watts, which in the US is the equivalent of about 4 light bulbs. We typically use 60-watt light bulbs here. Inside all that gold foil, which is thermal blanket, is everything needed for the trip: the communication system, the guidance system, the propulsion system, the power distribution system, the flight computers, the solid state storage, flash drives, all the electronics except for the instruments that are on the outside of the spacecraft where they have a clear view. And there are two of everything, a little bit like Noah's Ark. So there's a prime and a backup system for propulsion, prime and backup for communications, prime and backup for power distribution, prime and backup for propulsion, prime and backup for main computer, et cetera, on down the list. It's a very small spacecraft, and intentionally so. It's about the size of a baby grand piano. Fully fueled, it weighs 484 kilos. If you go to the National Air and Space Museum, where that model of New Horizons is, it's actually next to the Voyager spacecraft that's there in the same hall. And you will notice that the Voyager is enormous compared to New Horizons. It looks like a houseboat and a hamster next to each other. It really is dramatic. But just like the revolution in computing between the time of Voyager in the 70s and the time of New Horizons in the early 21st century, smaller doesn't mean less. It actually means more. This spacecraft is literally, no exaggeration, orders of magnitude more capable than Voyager. Its instrumentation is 30 years more advanced. As one example, the UV spectrometer, the ultraviolet spectrometer on Voyager, had 2 pixels. The UV spectrometer on New Horizons has 32,000. The infrared mapping spectrometer on Voyager had precisely 1 pixel. The New Horizons infrared mapping spectrometer has more than 500,000 and can stare at 500,000 places at once and develop simultaneous spectra at all of them. So you get place-to-place composition at every place on the planet simultaneously. And the same is true for the other types of instruments and for the capabilities of the spacecraft itself. But we built it to be small and lightweight because we wanted to put it on a big rocket and launch it as fast as possible to cross the solar system much more quickly than the Voyagers. And in fact, this was the fastest spacecraft ever launched, and to this day still is. Those of you who remember the Apollo program probably remember that Apollo astronauts launched at a speed of 25,000 miles an hour and took 3 days to reach the moon. By contrast, New Horizons reached the moon in slightly under 9 hours. It continued at that speed all the way across the solar system to Pluto, 3.5 billion miles away. And almost all of that propulsion was due to this rocket called an Atlas V. It was the largest available rocket in the world at that time in 2006. It's about a little over 70 meters tall. It's powered by 5 solid rocket boosters and a liquid oxygen, liquid hydrogen, high performance main stage and an upper stage that's also very powerful. And we topped it with a special purpose 3rd stage solid rocket motor. The nose cone or payload bay is about 70 feet or 20 something meters tall. And little New Horizons was about the equivalent of a hood ornament on that rocket. And we basically launched this giant rocket intended to launch school bus-sized spy satellites. We launched it more or less empty with New Horizons in it so that we get the fastest possible speed. And that all worked out. The launch was on the 19th of January, 2006, put us on a direct trajectory to Jupiter, no Earth gravity assist required. We arrived at Jupiter 13 months later, fastest spacecraft ever to reach Jupiter. In fact, then got a speed boost from that gravity assist and went on across the giant middle of our solar system where the giant planets lie to the 3rd zone, the Kuiper Belt. And so we flew from 2006 to 2015 across 2 US presidential administrations and a decade to reach the target Pluto and then to go on exploring in the Kuiper Belt. So this was really a mission of delayed gratification in many ways. It took 14 years to get it funded. It took 4.5 years to get it built and launched, and then a decade to cross the solar system. And so it was only in 2015 that it began delivering scientific results. When we launched on the trajectory to Jupiter, and you should be seeing an animation as we crossed the orbit of Mars in red and then intercepted Jupiter, We had to get the spacecraft checked out during those 13 months, all 7 scientific instruments checked out and calibrated. And then we used the Jupiter flyby as our practice run for Pluto. In fact, we conducted 700 scientific observations at Jupiter, more than we planned for Pluto, to put the spacecraft through a kind of stress test to weed out the bugs and the software and the flight operations techniques and everything else about the instrumentation and spacecraft. And that was very successful. After leaving Jupiter, we began to hibernate the spacecraft, meaning mostly put it to sleep. That saves money, saves wear and tear on the electronics. It saves fuel, as a matter of fact. And we hibernated the spacecraft, the first spacecraft to extensively hibernate. We hibernated 10 months a year, all the way to Pluto, with rare exception, and flew from Jupiter to the orbit of Saturn the very next year in 2008. We crossed the orbit of Uranus in 2011, and then on to the orbit of Neptune in 2014, intercepting Pluto in 2015 at a much closer range than this appears to be. We flew between the orbits of Pluto and its whole system of moons, very close to the planet. The flyby, as I said, took place in the summer of 2015, and it was actually a 6-month-long flyby. It began in January with navigation to home in on the target, beginning in about April, when we started to have very slightly better resolution than those blurry Hubble pictures. We began the science phase, but every week the images got better, and at the same time we were looking for hazards in our way, rings or moons, that might cause us to have to divert within the Pluto system to different aim points. And the flyby culminated on Bastille Day, the 14th of July in the year 2015. And worked out very well. It was really flawless and produced a spectacular scientific result. This is a little family portrait of Pluto in the lower right in true color. And for reference, for those who may not know, Pluto's diameter is about equivalent to the continental United States. If you put one limb of Pluto on the east coast of the United States, the other limb would be just west of where I live in Colorado, about 2/3 the way out to the west coast in California. Then Pluto has a very large moon that was discovered in 1978 called Charon. The pair constitute a true double planet with the balance point or barycenter between the two in free space. There's nothing else like it in our planetary system. It's a true double planet. Charon is the gray orb that's to the upper left of Pluto. And then Pluto has 4 small moons, or more properly, Pluto Charon have 4 small moons, 2 of which, the larger 2 of which, Nix and Hydra, are seen in the upper left-hand corner here by New Horizons. They're really just the size of counties. And the 2 smaller ones aren't in this image. We studied all 6 objects in the system with New Horizons using all 7 scientific instruments. The 4 smaller moons were discovered by our team during just before we launched, and then just during the flight of New Horizons, as we looked to make sure if there were more moons we wanted to know, so we could plan to point the scientific instruments at them. Now, because this talk is pretty compressed in time, I'm really only going to talk about results at Pluto. I'm not going to talk about the results from the small moons, although they were spectacular. And I will say just a word or two about the large moon Charon. I will tell you that this flyby was very challenging from a navigational standpoint for a number of reasons, one of which is that Pluto is tipped on its side, like the planet Uranus. We came out of the direction of the sun, of course, and had to fly by the plane in which all the satellites orbit simultaneously. So we had a very high time compression. Rather than encountering the objects one at a time as we progressed through the system, where we could focus on each individually, we had to bounce from one to the other, to the other, to the other, and back and forth with all these different instruments in order to get views of them before they were all gone. All on that single day of the 14th of July, 2015. In addition, we had very tight navigational constraints. We had to fly through a window in space that was only 60 by 100 kilometers, which is very large to drive a car through. But when you're aiming from 5 billion kilometers away at the Earth. That's a very tiny target and required very precise navigation. We also had to navigate very precisely in time, because in order to get all the imagery and spectroscopy done right, the spacecraft had to be told when it would arrive so it could point at the positions of all these moving targets, the planet and the satellites. And in fact, the tolerance was that we had to arrive within plus and minus 8 minutes after a 9.5-year journey. We actually delivered the spacecraft only 86 seconds off target, which is a real testament to the navigation team at Kinetics, who did this work, really spectacular work. This is the Pluto-Charon binary. These colors are enhanced or stretched in the computer to bring out detail of the redder and bluer and grayer and so forth regions on each. But what I want you to notice is that Pluto and Charon, although they've been together for 4.5 billion years in the same part of the solar system, with the same temperatures, same radiation environment, same bombardment environment, have evolved very differently, and they're very different objects. Pluto in the foreground is much more colorful. It has an atmosphere. It has much more varied geology on its surface. I'll show you more of that. It has a wide range of surface terrain ages, meaning that the planet is very active even to the current era. Charon, which has no sensible atmosphere, some interesting surface geology, but not nearly the variety, and no atmosphere and no weather systems that move volatiles, ices around on the surface. But it does have strange characteristics. This image shows you Charon in quite a bit more detail. You'll notice the big rift valley across the equator. It's about 10 times the size of the Grand Canyon on Earth. It's 10 times in length, width, and in depth. And everything that you're looking at, we know from our spectroscopy, is water ice, or water ice with small amounts of contaminants, mostly ammoniated compounds and some organic molecules that are not due to life, but due to the photoprocessing of gases from Pluto's atmosphere that run into Charon, stick to the cold surface, and then get photolyzed by solar ultraviolet light to make that red stain at the North Pole, for example. And the entire surface of Charon is very old, as old as the solar system, 4.5 billion years old, which we age date from the crater counts on the surface. Now I'll turn to Pluto, which is really the star of the show. And this is a mosaic of many images of Pluto made by New Horizons and wrapped onto a sphere in our computer to project it as it would look to you if you were aboard New Horizons near the time of closest approach. The big white or yellowish plane that you see is the western or left side of the heart on Pluto. It's a nitrogen glacier that is the largest glacier in our solar system. It's about a little bit larger than 1 million square kilometers, or for scale, that's larger than the states of Texas and Oklahoma in the United States combined. That glacier sits in an impact basin that actually raised large mountain ranges all around the rim. And if you can see my cursor, I'm pointing to the mountain ranges along the rim that were raised by that impact before the basin was filled with glacier. These are very tall mountains. They're taller than almost all mountains on the Earth. We use imperial units, so 20,000 feet, and that means that they're 4, almost 5 kilometers high in many cases. All of those mountains, we know from compositional spectroscopy, are made of water ice, which is the most common constructional material in the outer solar system. But they're frosted with different kinds of materials, and you see the different colors. Most of what you're seeing that's yellowish or whitish is nitrogen ice. By the way, that's the same stuff you're breathing. It's just that it's so cold, about 40 Kelvin on Pluto's surface, that the nitrogen snows out onto the surface. The depth of the snow in the glacier is kilometers deep. This is a very vast piece of real estate, this glacier called Sputnik. The redder things that you see are the results of the methane in Pluto's atmosphere that also snows on the surface, interacting with the same ultraviolet sunlight that made the red stain I showed you on Sharon's North Pole, and creates long-chain hydrocarbons and other molecules called nitriles that you see as those reddish stains across some portions of the surface, and the blacker stuff as well. And then there are other compositional elements to the surface, including, again, ammonia, water ice that we see, the methane that I mentioned, the nitrogen that I mentioned, but also carbon monoxide and carbon dioxide ices. Really a spectacular place and very highly varied geology, but it also has an atmosphere. This is a true color image of the atmosphere made by New Horizons. That atmosphere extends about 500 kilometers into space and is very highly vertically structured. You can see the haze layers, the concentric haze layers here above the sunlit limb. The streaks that you see on the surface are actually equivalent to terrestrial corpuscular rays. If you've seen rays of sunlight between mountains somewhere on the Earth, the same phenomenology is taking place here. Those are rays of sunlight at the evening terminator through Pluto's hazy atmosphere. And the shadows, the dark zones are due to the shadows of mountains, and the brighter ones are the rays of sunlight between mountains. But the atmosphere is the star in this image. It's mostly made of nitrogen, just like the Earth's atmosphere. It is blue, just like the Earth's atmosphere, but it is dramatically colder. It's very close to absolute zero on Pluto's surface, and the atmosphere is not much warmer. The atmosphere is laced with these haze particles that make it visible to us. But the nitrogen has a very low pressure, much less than here on the Earth. It's about 10 microbars. That's 1 part in 10 to the 5th of the pressure at sea level on Earth. It's about equivalent to the pressure of the Earth's atmosphere in the mesosphere, 80 kilometers above our heads. That atmosphere also contains a whole variety of minor constituents, including carbon monoxide, methane, that's natural gas, a whole wide range of photochemical byproducts made of carbon and nitrogen and oxygen molecules that include things like ethane, ethylene, acetylene, all in the atmosphere. There's no free oxygen, so it's never going to catch on fire. There's no way to make it burn. But there are also interesting constituents like hydrogen sulfide. I'm going to show you a number of views of Pluto's surface now. This is a region of the surface where the green square, what you're looking at, is about the size of where I live in western Colorado. And these are mountain ranges out in the Kuiper Belt that you can see that have similar heights to the Rocky Mountains and are snow-capped, just like the Rocky Mountains in winter. But these snows are not water. The water isn't volatile at those low temperatures on Pluto. We actually put lots and lots of pixels on these snow caps with our infrared spectrometer. This is methane snow, CH4, that plates out at high altitude in these regions that you see. But it's white, and so it's very reminiscent of the snow caps we have of water ice on the Earth. This is another kind of mountainous terrain on Pluto. It's actually unlike any other mountain building terrains anywhere we've seen in the solar system. We call it snakeskin or bladed terrain. These bladed mountains are individually several kilometers apart. This is a region of several hundred kilometers in extent in which all the mountains are aligned together. They have vertical extents of about 1 kilometer, and they're made of methane ice, solid methane crystals. It's kind of a sci-fi world where we have giant glaciers and avalanches and ice volcanoes and strange kinds of geology that we saw nowhere else. This is a picture near the terminator, as you can tell. So the vertical relief is very easy to see. But this kind of geology had never been spotted on any of the icy satellites or other worlds of the solar system. This is a picture that's actually just on the borderland, slightly to the west of the big glacier Sputnik. but it's full of craters. And this means that it's very old. And we can age date this just like we age dated Charon's surface to be 4.5 billion years old. So it's as old as the solar system, as old as the planet. But immediately next to it on the glacier, there are no craters, zero. Over 1.1 million square kilometers at the highest resolutions, which, by the way, are 50 times higher resolution than the first missions to Mars revealed. We have imagery that goes down to as little as 70 meters per pixel. And across that entire 1.1 million square kilometers, there is not a single crater, which allows us to determine an upper limit to the age of this region, the size of Texas and Oklahoma combined. And it's just a few million years old, perhaps 10 million in the extreme. That means it's 1,000 times younger than the planet. It means that Pluto is creating these enormous geological structures like the glacier. Million square kilometers created yesterday geologically. This is an image which is color-coded for altitude, and the reds and the greens are very high. You can see the scale in the upper right, 6 kilometers above the lower terrains that are purple. And I show this one because it's another kind of activity on Pluto's surface. Out of that mountain range down a chute came a lot of material due to an avalanche that pooled out on top of the glacier. I want you to notice there are no craters there either. That means that the avalanche that created this area, and by the way, the diameter of that circular pond caused by this avalanche, that is the diameter of the regions inscribed by the red arrows, is about the scale of the city of London. This is a big avalanche. It has no craters on it. It is geologically recent as well. And we found ice volcanoes the size of Mauna Loa and Mauna Kea in Hawaii, just as high and just as large, 100 kilometers across, 4 kilometers high almost, and with 0 craters on their flanks. So this is yet another example of is another line of evidence that Pluto's creating massive geological terrains in the present day. And this was not only not expected, the textbook said it can't happen. The understanding of geophysics that we thought we had from the exploration of the closer planets was upended by the exploration of Pluto. Somehow this little planet, which clearly doesn't read the textbooks, is creating geology on massive scales, and no human really knows why or how it's able to not cool off and run its geological engine billions of years later. There are a lot of good ideas, but we don't have enough data to really know which one is right. When we go back someday with an orbiter, we know how to find out which idea is right, or maybe none of our ideas are right and there'll be a new idea. But we need to take different kinds of instrumentation that we didn't have on New Horizons to pin that down. There are also many lines of evidence that are circumstantial, but which form a very strong case that Pluto, like Europa and Enceladus, has a water ice ocean beneath everything you're seeing, a global water ice ocean, which may even be habitable for biology. Someday we will learn about that. But this picture, which is the last detailed picture I will show you, is one of my favorites, not my very favorite, but one of them. In the center of the image towards the top, you see that oval region. It is actually a frozen lake of nitrogen. It has a shoreline around it. We have stereoscopic imaging to allow us to reconstruct the topography, and it's sitting in a hanging mountain valley. But the interesting thing about this lake, which is about 30 kilometers in length along the major axis, is that at Pluto's present atmospheric conditions, liquid nitrogen cannot exist. If you look in the phase diagram of nitrogen, the pressure and temperature aren't at a place where liquids can persist on the surface. So this is pretty good forensic evidence that Pluto had a much thicker atmosphere, thicker than Mars's atmosphere in the ancient past, one or more times. And that, it's kind of like a crime scene in a detective movie. We don't see the culprit, but we see evidence of the culprit here. It's telling us that Pluto's atmosphere was one or more times very thick, 100 times thicker than it is now. This is a movie made from New Horizons images, starting at the North Pole of Pluto and extending down onto the glacier over that rectangular region. We're going to go through it in a little over 30 seconds. So fasten your seatbelts. And you can see terrain at Pluto, even up in the North Pole, where you can look inside the surface at craters that are windows in the interior. You can see those rectilinear tracks across the surface that are probably caused by dust devils in the past. And then mountain ranges. These are made of water ice, but frosted in nitrogen. This is a scale bar, 6 miles or 10 kilometers in the lower right. And after we cross the shoreline off the mountains, you're on the glacier where you can see dune fields and convection cells and many other kinds of interesting detail. We have now flown over almost 1,500 kilometers in that 30 seconds of Pluto, as shown by this little movie. When we did that flyby, it was a worldwide media sensation. For almost half the people on Earth, it was the first time they'd ever seen a new planet explored. Because the Voyagers were very far in the past, in the 1980s. And 40% of the people in the United States, according to a census, were either not alive or not old enough to remember the Voyager encounters. And so this thing was all over the magazines, all over television, all over the web, 450 some odd newspapers across the world, on every continent, including Antarctica, the very next day, above the fold, on the cover. Really stunning how many people are nerdier than they think and are interested in exploration, and particularly the exploration of our solar system. And for us, it was viscerally demonstrated. Thousands of people came to our mission control. This is a picture. If you can see my cursor moving, you can see the clock. It's 4 seconds before closest approach to Pluto. And this room was filled with thousands of people. It was kind of a Woodstock moment for space geeks. And for my team that had worked on this since 2001, this is an actual candid shot from behind by a single member of the press that we allowed in the room when they saw the first high-res image of Pluto. It was very emotional. We had one shot at this flyby. There's no second spacecraft like the Voyagers to get it right if you missed. There was no going back. And actually, the entire flyby was conducted flawlessly, thanks to a lot of practice and an amazingly engineered spacecraft and scientific payload. And I think you can see just from this image that the energy in the room for people who had put huge portion of their lives and their careers on the line from 2001 to 2015 to make this all work. This is my favorite picture of the entire flyby, not because it's the best scientifically, but because it's Pluto backlit by the sun, which can only be achieved when you've flown past Pluto and you are looking back from the far side. And to me, this is the equivalent of the Apollo Earthrise image. I worked on this from 1988 to 2015, and so did lots of other people. And this is the we did it picture. For me, this is it. This is putting a spacecraft on the far side of Pluto. And as I said, it was a blur getting it built, but this team did it right. There was a huge commitment of time and personal sacrifice in this team. We hired people telling them we expected that, and they delivered. And as I said, for 4.5 years, it was 7 days a week for all of us. It was 52 weeks a year. There were no excuses for holidays or anything else. And we had to do it on this low budget that meant we could only send one spacecraft. So it had to work on the first try for 10 years to get across the solar system. And then in a matter of days to flash through the Pluto system. That commitment, I think, is a testament to what humans can do when they work in big teams. They do things larger than life that no single human being could pull off, but in big teams, humans can do amazing things. It's also due to the fact that we covered every base in the engineering of the spacecraft and the instruments and the software engineering and the flyby sequence that we wrote and practiced over and over and over again, even practiced it on the spacecraft out in the deep outer solar system multiple times before we got to Pluto to work all the bugs out. We tried to think of everything. We developed hundreds of malfunction procedures, fortunately, none of which were needed. We did have one cathartic moment where the spacecraft reset 10 days before flyby, but our mission control team saved the day in a matter of 48 hours and got it back on track. We programmed the spacecraft to be able to do things that we didn't have the reaction time to do from Earth, to handle hundreds of immediate faults like fuel leaks or over temperatures or computer errors. Fortunately, almost none of that was needed. We covered every base. We did all of our homework, and it paid off. And more than anything, that's due to the teamwork that I was just telling you about. Just ordinary people. This is the flight crew of New Horizons. This is everybody who was involved in flying this spacecraft. This picture was taken the week of the flyby at the Johns Hopkins Applied Physics Lab in Maryland on the East Coast of the United States. This is our mission control team, our engineering team, science team, and the project management team, public affairs team, everybody, barely over 100 individuals, just ordinary people who worked very, very hard for a long time, who poured all their smarts into this and have been and still are, in many cases, the crew of New Horizons. I will end with this slide. Pluto really has become the other red planet in our solar system, as complex as the Earth or Mars, and defying the textbooks in terms of both its complexity and its level of activity. We did not expect. Since that flyby in 2015, New Horizons has gone out in the Kuiper Belt, flown by a primordial building block of the planets called Arrokoth in 2019, has made many other discoveries. We've now studied almost 40 Kuiper Belt objects with New Horizons. We continue to do that. The spacecraft is healthy. It has fuel and power to run to mid-century. The main consumable that we worry about is money, that we continue to be funded. But we have a perfectly healthy spacecraft, and all 7 scientific instruments are working. And I just can't tell you how proud I am of this team. And I want to thank you for inviting me here today. So we have a few minutes for questions if I can answer any.
That's absolutely fantastic, Alan. Thank you so much for that.
My pleasure.
Yep, absolutely brilliant. Yes, thank
Yeah,
you.
and it's so marvelous, of course,
Thank you.
to get the word from the person really concerned with it and get the behind the scenes knowledge that no one else will have. So does anybody have any questions that they would like to put to Alan? We did ask for you to put things in the chat, but Alex, if you would like to unmute yourself and ask yours.
Yeah, the chat is disabled. I had a few questions. You mentioned publishing multiple papers on Pluto before New Horizons. What were you actually able to say about it? And then how long was the A list that you needed to be at the top of?
Those are great questions. Thank you. I published several dozen scientific papers, not first author of all of them, but first author of many. Some of them were theory and modeling, and others were observations that were telling us about Pluto's surface composition, its atmospheric composition, constraining its pressure. The papers with the Hubble images, primarily some searches for satellites, and ultimately in 2005, the discovery of Nixon Hydra. All that was before New Horizons. As to the A-list, typically when we do these decadal surveys, there are about 100 missions that are proposed, of which 2 or 3 get to the top of the list and get funded. So it's a stiff competition.
And why did you originally select the underdog team?
I'm sorry?
Why did you originally select the underdog team?
Well, I didn't select, I was selected. And NASA has never told us why. I mean, we know that we had higher scores on the proposal. But the details of whether that was about thinking we were more likely to deliver on cost or more committed or had better designs or what have you, have never been divulged.
No, I thought you mentioned you chose to lead the underdog team.
You asked why. I understand your question better now. Thank you. Yes, well, this is a true story. The day that NASA announced there would be a competition for teams to lead the exploration of Pluto, I received 2 phone calls to lead proposals, one from the Jet Propulsion Lab and one from the Applied Physics Lab. Both laboratory directors called me the same day, 19th of December, 2000, within hours of NASA announcing. They said, would you lead our teams? And I thought, well, this is a Hobson's choice. JPL had been in charge of 4 previous Pluto missions, none of which had gotten off the drawing board. But they had all this experience all the way back to the early Mariner days of successfully exploring the solar system. The Applied Physics Lab, by contrast, had done precisely 1 mission in the solar system. Although they'd done hundreds of missions in Earth orbit, they never experienced only 1 planetary mission. It was to a near-Earth asteroid, literally around the corner compared to going to Pluto. So they had very much less experience, but they seemed much more committed. And I asked the next day, the 20th of December, I asked both laboratory directors the same 3 questions to make my choice. I asked, would you give me your A team for the proposal and the project? Your very best. I get the pick of the litter. I asked, if we win it, will you promise to fight for it and keep it? And third, will you do whatever it takes to actually get this off the drawing board to a launch pad and across the solar system? And unfortunately, the JPL director hemmed and hawed on all 3 questions. He said, well, you know, we're actually putting in 2 proposals for Pluto. You're going to have to split the A-list with another team. And, you know, we work for NASA, and we can only fight so much because we're also on NASA's team. And so forth and so on. And the guy from the director of the Applied Physics Lab said, you're my only team. You're going to get the best people. This is reputational for us. We want to win it at all costs. If we win it, we will fight to keep it at all costs. And you tell me what you need and you'll get it. And that's what they did for 20 years.
Thank you.
Thanks. Kevin, would you like to ask yours?
Yes, indeed. Thank you, Alan, for such an amazing talk. I wanted to ask what the best ideas are for how Pluto is still geologically active, given its small size after all billions of years.
Yeah, great question. There are a lot of things we know doesn't work. Like, a lot of people would like to think that it's the tidal despinning of Pluto and Charon as a binary that generated a lot of heat, but all of it in the ancient past. And so that can't be the energy source today. I think
Are they tidally locked?
They are. Yeah.
So yes.
Spin, orbit, resonance, yes. 6.387 days. The idea that I like the best has to do with the ocean. Pluto's global ocean is essentially a battery, a capacitor. It stores energy, and as it freezes, it releases latent heat. And when you do the back of the envelope calculation, that's the right order of magnitude of heat to generate the kind of geology that we see. Whether that's actually the right idea or not, I don't know. But I think there's a wonderful symmetry in that. I'd like to see it be the right idea, but we need to go learn more about the ocean to see if it's really doing that or if there's some other better idea. And there's several out in the scientific literature besides that. That's just my favorite.
Thank you.
Yeah.
Anyone else like to ask a question? You want to raise your hand?
Bosley's got a question in the chat.
Yeah. Okay.
Yeah.
My question, you mentioned those methane ice ridges and how they're all aligned.
Yeah.
Do we have any idea why they might be like that? Is that anything to do with the heating you're just talking about?
I have not heard that suggested. There are 2. First of all, I should tell you that those mountains that we see on the Terminator, which I showed you, turn out to be very widespread across Pluto. I just showed you one example. We see it even on the far side where we don't have as good of an imagery, but the data that we do have indicates that this form of geology is very widespread around Pluto's equator. There are 2 basic ideas. We don't know which one is right. One is that this was formerly big sheets of methane, frozen methane, which were scoured by winds, perhaps when there was a thicker atmosphere. An erosionary process created all the valleys between them, and then the winds are coming from a certain direction, and then you end up with aligned ridges. Why there would be ridges as opposed to just grinding it all down is a good question. The other idea is that the blades are accretional, that the methane was precipitating out of the atmosphere, and where there were seeds of topography, they kind of fed on themselves. I'm not a geologist, so I can't really tell you the ins and outs and details of that, the pros and cons for each of the two, but those are the two primary ideas for how they were made.
Okay, thank you.
Alan, I'm very conscious of the time, so everyone else, I'm sure there are a number of other questions you'd like to ask. If you send them to me at meetings@fedastro.org.uk, I will pass them on to Alan for him to look at in due course.
And give it a try. If you send me 50 questions, then that's very time consuming.
Well,
send me 3 or 4.
Yes.
I can certainly handle it, but there's a lot of you there. There's 56 people, and every person has 2 or 3 questions.
I'm sure. On behalf of all of us here of the FAS, I'd like to express our thanks to you for giving up your time for us. It's been quite remarkable, and I'm sure for us a unique experience.
Well, it was a pleasure.
Alan,
thank you for inviting.
Thank you very much indeed.
Thank you. Hope you have a great rest of the meeting. And if you recorded, send me the link, because I want to hear what you have to say, even though I have to go.
Of course, we'll send you the link.
I'd love to do that.
Yeah, and just before you go, I'd just like to quickly show something, because well, there used to be car stickers that you could put on saying my other car is a Porsche and whatnot. Well, because my name is actually on the New Horizons craft, so I created a sign which I had in the back window of my car saying, well, sorry, where's it gone? All right, let's stop that. Let's try again. Share. Thank you. Right. So it said, my other vehicle has gone to Pluto. And yet it was only at the beginning of this year that I discovered that you and I have a similar sense of humor, because I found this photo of
There you go.
having done the same thing, but yours, well, it's more accurate for you because you actually did the exploration.
Well, I'll take 1 minute and tell you a story.
Go on, please.
A few months after launch, I got a phone call from one of the engineers on the New Horizons mission control team. Her name is Val Malder. And she just called me randomly and said, hey, Alan, I'm in a traffic jam here in Maryland, and I'm staring at the back of a guy's truck. And apparently he has a boat, and he has a bumper sticker about the boat. I have a great idea for a New Horizons bumper sticker. And it was really Val's idea that we made that bumper sticker, and they're very popular. We've given out thousands and thousands of them. And congratulations for having the same idea, Jerry. A lot of people signed that CD-ROM back in the day. I think 535,000 people signed on with their names to go to Pluto. Glad you're one of them.
Yeah.
Fine. Well, thank you very much for that. And we'll let you go to see the rest of your family, including the new addition to your family.
Yes, born this morning. Thank you very much.
Again. Right.
Bye all.
Thank you. Thank you, Alan.
And for everyone else then, we'll continue with the second half of our session today. So I'm the meetings organizer, as I said earlier. I'm also a a freelance space presenter, and I've given presentations on astronomy and space exploration going right back to 1969. So I've been doing this for over 55 years, but for the last 20 years, it's been what I do for a living. And one of my most popular presentations is about planet Pluto, and particularly on the question of, is Pluto a planet? Now, this is my most controversial presentation, so I should show this notice. I've actually had one professional astronomer say that this contains information that I should not be saying. And so, yeah, I think that's great. So here are the discovery plates from 1930 of Pluto, showing it in one position and then in this position 6 days later. Knowing the angular distance it had travelled in that time, it was possible to work out its orbit and show that it was way beyond Neptune, and made headlines. And I talked about this in more detail 3 weeks ago when we had Mike Brown as our guest speaker. So that gave us a solar system with 9 planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto. And if you weren't a space geek like me, who could just name them all straight off, you could use a mnemonic. You take the first letter of the names of each of the planets and construct a sentence that starts, that made up of words that start with those letters. So many vicious elephants munch jam sandwiches, unusually no peanuts. Or one that I made up for Valentine's Day: Mary's violet eyes make John sit up nights pining. There is one that you can't use in schools, which is Mary's virgin explanation made Joseph suspect upstairs neighbour Peter. But one that does go down very well in schools is my very excited mouse jumped straight up Nanny's pants. But the one that I always liked from the beginning was my very educated mother just served up 9 planets. It does exactly what it says on the tin, but we don't have 9 planets anymore. So here are, on the top line, some that should be familiar and some less familiar new discoveries. And the one I want to particularly point out to you is at the bottom right, 2003 UB313. Now, it's obviously not its name. That was a reference describing when it was discovered. But look at the size compared to Pluto. We originally thought that it was bigger than Pluto. We now believe it's slightly smaller, but has more mass. But the question still stands. If Pluto is a planet, surely isn't this a planet as well? And what about the others? And how do you know? Well, first of all, you have to know what a planet is. And rather surprisingly, there was no formal definition of a planet up till then. I'm sure many of you remember astronomy books when you were younger, saying that stars give out light, which is why we can see them, but we only see planets because they reflect light from stars. But that's it. So this was a question that was discussed by the International Astronomical Union, which is made up of over 10,000 professional astronomers from around the world. And every 3 years, they have a full conference, which in 2006 was held in, and this was one of the objects they discussed. So here was our original solar system, and a proposal was put forward, which would mean that the solar system should include Ceres, the largest of the asteroids, and I'll explain why, and Pluto and 2003 UB313. Now, Mike Brown, who led the team that discovered 2003 UB313, got so fed up of having to say that over and over before it was given an official name that he came up with a nickname, Xena. And yes, it really was named after the warrior princess from the TV series, which should be no surprise because, of course, you know that astronomers do like observing heavenly bodies. Sorry. So why Ceres, though? Well, because the proposal for the definition of a planet said that an object had to be in orbit around the sun, it had to be round, and Ceres, the largest of the asteroids, is definitely round. Now, there are other things that we'll come on to. Meanwhile, later on, Xena was given a official name of Eris, the goddess of discord and disharmony and strife. And considering the huge controversy and the argument it produced, it's the perfect name. So here is a picture from the General Assembly with the vote being taken on the proposal. And the definition read as such: a planet is a celestial body that is in orbit around the sun and is not a star nor a satellite of a planet. And it has sufficient mass for its self-gravity to overcome rigid body forces so that it assumes a hydrostatic equilibrium, so it'll have a nearly round shape, and also that it has cleared the neighborhood around its orbit. So you need to pass all three criteria to be a planet. If you pass the first two but fail the third, then you'll fall into a new category, a dwarf planet. So here is the vote being taken, and it looks like there's quite a lot, but in fact it was a relatively small number. And one problem is that all of the votes are only taken on the last day of the Congress, and by then a number of the 1,200 delegates had already gone home, so there were only about 480 people who voted, and 287 were in favour out of the over 10,000 members. So really, you can hardly say that the IAU voted on this. It was only a very small number on them, less a percentage than would be needed to pass a bill in the House of Commons. So we had then, as a result of this, 8 main planets or classical planets and 3 dwarf planets. And since then, 2 more objects, Haumea and Makemake, were added to that list. So Mike Brown's teams have actually discovered more and more and more objects. So he came up with two diagrams, one showing the old solar system and one showing the new one. Well, since that vote was taken, we have actually had another dwarf planet added, 2015 RR245. So although it was discovered 10 years ago, it still has not been given an official name. And then, so there it is from previous images which were checked back on. This is actually of 2017 OF201, first seen, as you can see there, in 2011. And this also hasn't been given an official name. There is a third object that has been classified as a dwarf planet, and that is Quawa, which was on that first image I showed of new objects. So that means that we have 8 dwarf planets, 9 if we include Charon as well as Pluto. And the original proposal to the IAU included Pluto and Charon. So although the first criteria says that a planet cannot be a satellite of a planet, well, it cannot orbit a planet, Charon does not orbit Pluto, because whereas with the Earth, the moon is only 1/81 of the mass of the Earth, and because of that and its distance, if you draw a line from the center of the Earth to the center of the moon and divide it into 81 plus 1 and then move out 1 unit, you will be about 1600 miles below the surface of the Earth. So it is true to say that the moon orbits the Earth. And the similar situation is true with every other moon and planet in the solar system, with just one exception: Pluto and Charon. Pluto is only 10 times the mass of Charon. And if you draw a line from center to center, divide it into 10 plus 1, 11, move out 1 unit, you are out in space. And both Pluto and Charon orbit this point, which is called a barycenter. And as New Horizons approached the Pluto system, you could actually see that. Pluto itself was orbiting a point in space along with Charon. So that's why they were proposed as a double planet. And people at the IAU figuratively threw their hands in the air and said, we can't have that, for no good reason that I can understand. So if we include Charon, we have 9 dwarf planets and 8 main planets, making a total of 17 objects. So what is a dwarf planet? Well, this, I'm sure some of you will recognize, is a scene classic Time Bandits with this group of actors. And one that I want to point out is this one, who also played R2-D2. This is Kenny Baker, who I've met a couple of times before he passed away. And he might be, along with the others, described as a dwarf. But when I ask audiences, but what is he, basically? And then they realize, yeah, he's a human being, right? He's not some other kind of creature. So if a dwarf human is a human, why is it that the IAU said a dwarf planet is not a planet? What about this? So obviously it's a star. It's actually our star. It's the sun. But more than that, it is a type G2 yellow dwarf star. So does that mean because it's a dwarf star, it is a star at all? No, it is a star. There is not a single professional astronomer, not a single member of the IAU, not a single person who took part in that vote who will say our sun is not a star. And what about this? It's a galaxy, but actually it's a dwarf galaxy. And so is this. And so is this. Sorry, when it comes up. So let's say that astronomy is special and it doesn't need to follow the rules of every other science, which will say that a dwarf Nigerian goat is a goat and a dwarf beech tree is a tree and a dwarf human is a human. So if they are special and if they say that a dwarf planet is not a planet, should we accept that? Well, maybe astronomy doesn't need to follow the rules of every other science, and be consistent with them. But it should be consistent with itself. So if a dwarf star is a star and a dwarf galaxy is a galaxy, then a dwarf planet is a planet, and that's it. No further questions needs to be asked. But it goes beyond that. So it would be good if the IAU had labelled them like this. There are the 4 terrestrial planets, the 4 gas or ice giant planets, and there are the dwarf planets. And that way it would be obvious that there are 3 major types of planets, and everyone will accept that. They are all forms of planets. But no, they didn't do that. So what about this? Well, it's a tree, yeah? And these are all trees. And it doesn't matter if they're by themselves or whether they have grown in an area which is clear of other objects. They're all trees. So what do the public think of this? They were not happy. And the public view, as you can see, was Pluto definitely is a planet. Well, if we come back to the definition, which was changed, that's why it says revised definition. The original proposal said a planet is a celestial body that is in orbit around a star, and it was amended to orbit around the sun, which means, first of all, this is only a definition for objects in our solar system, and also that the 6,000 other objects and more that we have discovered elsewhere are not planets because they don't orbit the sun. Well, having gone through various issues with the wording of the definition, let's look at this. So the sun and each planet also has a barycenter, and that will be, for the most of them, not only inside the sun but very close to the center. However, if we look at Jupiter and take the mass of Jupiter compared to the Sun and find its barycenter, it is actually 46,000 miles above the surface of the Sun. So like Pluto and Charon, the Sun and Jupiter orbit that point in space. As a result, the Sun from a distance will be seen to wobble from side to side, and we have seen this with other stars, and consequently we have deduced that they are being orbited by a massive planet, and by timing it we can work out the duration of that planet's orbit. But if we look at this first of the three criteria, Jupiter obviously is not in orbit around the Sun, so it fails that. And yet it is accepted as a main planet by the IAU. So what they're effectively saying is, yeah, we know it fails that, but we're going to ignore it. Well, sorry, you can't do that. If this is your criteria and you ignore it for one object, you have to ignore it for all of them, which means you have to remove this from the definition. So what about the next part? It has to be in hydrostatic equilibrium and have a nearly round shape. Well, here's Haumea, which, as you can see, does not by any stretch of the imagination have a nearly twice as long in one direction as it is in another. But having a nearly round shape is intended to be a consequence of being in hydrostatic equilibrium, and amazingly Haumea is. So that isn't an issue. This is Mercury, which is much, much larger than Haumea and is round, but it is not in hydrostatic equilibrium. And there are some papers which say that Venus isn't either. So again, we have an object that fails the criteria but is accepted by the IAU as a planet. So again, they're saying, yeah, we know it fails, but we're ignoring it. And the result is you have to remove that criteria as well. And what about the third? Clearing the neighbourhood around its orbit. Well, it was assumed that objects with a good amount of gravity would have cleared other things out of their orbits. What they totally failed to consider was that an object with high gravity would attract objects into its orbit. So here the outer ring is the orbit of Jupiter, and centered around the Lagrange L4 and L5 points are what are known as the Trojan asteroids, and there are thousands and thousands of them. So Jupiter, more than any other object in the solar system, has failed to clear its orbit, which means it would be a dwarf planet despite being 1,300 times the volume of the Earth. But in fact, because it fails that entirely and doesn't go around the Sun, it is not a planet at all. So as you can see, the only valid statement from the IAU definition is a planet is a celestial body. So I actually designed and printed some t-shirts which look like this, and if anybody would like one, then write to me at that email address. They're £15 plus a small amount of postage, obviously, but I've worn that when giving the full version of this presentation, and goes down very well. So the bottom line is, regarding the question, is Pluto a planet? Well, if we just come back to the first clause, dwarf planet, what does that itself mean? Well, planet is a noun. It says what the object is. Dwarf is an adjective. It says what type of object that is. So by labeling Pluto and these other things as a dwarf planet, the IAU is effectively saying it is a small planet. And if they didn't want them to be known as planets, they shouldn't have labelled them that way. They should have given them a completely different term. I came up with one, Hoogly Fliff. So if Pluto was a Hoogly Fliff, it wouldn't be a planet. But no, it is a dwarf planet, which means it is a planet. And it is one of the 17 planets of our solar system. So if this comes up in a conversation with anyone, you can say, yes, there are 17 planets. Jerry has said so. And that's it. So, if anyone has any questions that they'd like to ask about that, I'll be happy to take them.
Thank
Paul,
you very much.
yes.
Thank you.
Hello there, Jerry. Thanks very much for your controversial talk. I have to say I disagree with you on many points, as I'm sure perhaps several others here do, and there may be some who agree with you. So that's why controversial rather than...
Hence my statement right at the beginning.
Excuse me, I have a dog on my lap. So, I mean, I think you've done a very good job of torturing the semantics rather. I mean, for example, the concept of Jupiter not orbiting the sun because they actually orbit around a common barycenter. I think that's a little bit pointless, because if the sun weren't there, then Jupiter would fly off. So it quite clearly is gravitationally bound to the sun as its principal host.
Yes, no, I that. And
in the same way, if Pluto weren't there, Charon would fly off.
No.
It may still be bound to the sun, but it wouldn't be bound to Pluto anymore. So I think the idea of using the barycenter, or as being outside the radius of the host body, is perhaps a little flimsy, because what if, for example, the sun had the same mass that it does, but were less dense and were larger? Then the barycenter would lie within the surface. I mean, I looked it up. It's only 7% outside. So sorry, 7% of the sun's radius outside of the sun. So the sun would only need to be slightly less dense for your argument to not be true. So I think that's the first one. I don't think the barycenter argument works. Secondly, the word dwarf is being used in all these contexts as an adjective. You know, so you know, a big man or a brown cat or whatever. It's the same way, a dwarf planet. Yes, it's a planet, but you're using the word dwarf to discriminate between different sorts of planets. So it's not necessarily saying dwarf, sorry, that it isn't a celestial body that's a planet, but it's a descriptive of it being a small version of that, and therefore separate from the main planets. So I would agree with, in a sense, it being used in a descriptive sense, but it's being used to denote a different category. Also, your other argument about it being voted on by a small number of people, you have to remember that the IAU General Assembly of 1,200 odd people, you said, is a getting together of people with lots of different disciplines within astronomy. So there would have been cosmologists there, there would have been infrared astronomers there, and so on and so on. All the different divisions in parallel meetings, etc. And one of those sections would have been the kernel of professionals who would have the expertise on whether or not to decide on whether Pluto is a planet or not. So the fact that many of them have left just means that maybe their sessions have all come to an end and they've gone home because the discussion about Pluto wasn't part of their professional capacity. So I don't think that argument really holds, that they weren't
No.
enough to make it worthwhile. So I thank you for your talk. Certainly
Okay.
controversial, certainly interesting, but I have to say I disagree with you.
Okay,
Thank you.
well, let's take the last point. There were discussions which took place on previous days, but as I said, all the votes can only be taken on the last day and only by people who are physically present, which was a very small percentage of the IAU membership. It's been said since that the vote really should have been decided by planetary scientists rather than astronomers, but that's another thing. As for the barycenter, I said that Pluto is only 10 times the mass of Charon. Suppose they were equal mass. The barycenter would then be halfway between them, and they would be a double planet, no questions asked. So the real question is, at what point does it become a double planet or a planet and a satellite? And what I have
or indeed a double dwarf planet.
well, that's really. So I've taken the physical characteristics rather than say it has to be within 10,000 miles of a planet's surface. I mean, that is a man-made value. So I'm just looking at the physical properties. Is it above the surface or below? And I'm also quite happy to say that accurately, Charon does go around Pluto, and obviously Jupiter does go around the Sun, but technically it does not orbit the Sun. And that was the word used in the definition, so that's what we have to go by. So, Alex, so let's move on to you.
You mentioned that a professional astronomer told you your talk included stuff you shouldn't be saying. What was that?
You don't happen to think that I'm going to say who that was?
No. What was that?
But no, he just said there is information.
Yeah.
In the presentation which I shouldn't be saying, and he didn't
Specify.
explicitly pick anything out.
Right. Just to respond to what Paul said, I do agree with you on all the points. So in terms of barycenter, yeah, if two objects of equal mass have a barycenter right in the middle, then can you say that one orbits the other? I mean, Paul was saying that if the sun disappeared, then Jupiter would fly fall. Yes, that's the same for any two objects that rotate around a barycenter.
Yes.
But I think the key point has to be, for one object to be described as orbiting another, then the barycenter has to be inside the other object.
Yes.
That is the only boundary point that is not completely arbitrary.
That's it.
And then
so
in terms of
Jupiter goes around the sun, but it doesn't orbit.
Yeah. In terms of the IAU vote, I mean, yes, you can talk about who the voting body should be, but as it stands, there was a vote at the IAU, and it's been described as the IAU voting on it, but it was indeed a tiny fraction of the vote. Is it really reasonable to say that the IAU, as a massive organization, has voted when only a tiny fraction actually even voted? Then a proportion of that only voted in favor.
Yeah.
And then the other point was about dwarf planets, which should, and the whole point that Joe was making is that dwarf planets are planets. Dwarf is just an adjective, a descriptor. Whereas my understanding is that the official position is that dwarf planets are not planets.
Yeah.
The dwarf planet is an entirely separate category rather than a subcategory.
Yes.
And the point that Joe is making is that it shouldn't be a separate category, it should be a subcategory of planets.
Yes. Yeah, which is why I said if they didn't want them to be known as planets, they should have given them a different label. In fact, in my full presentation, I go a bit further and suggest that whoever said who came up with the statement a dwarf planet is not a planet, and whoever approved that wording to be published do not really understand English.
Well,
If I
tell you
could
what,
just,
Jerry.
if I could just quickly chip in, I mean,
Yes.
in response to the comment Alex made, where is the edge of the sun? I mean, is it the photosphere? Because that's just what you can see. But of course, there's the chromosphere, and then you've got how far the solar wind comes out to the magnetopause. At what point does the sun end? Now,
Okay.
okay, we happen to be
Well,
able to see the photosphere,
yes.
but of course, if you were to look at the sun at different wavelengths, you will have a different radius for the sun.
Okay.
So
if we,
it's not a hard surface. So
no. If we look at the Earth, and the Earth has a magnetic field, so if we were to view the Earth and trace its magnetic field, then that would be much larger than the physical presence. So looking at what is essentially the physical presence, that is out to the photosphere, then that is, I would say, regarded as that. Of course, the situation will completely change when the sun runs out of most of its fuel and expands, and then well, it will also become less dense, so all the planet's orbits will enlarge, but the sun probably will not quite reach as far as the Earth, because we will have moved further out as well. But it's most likely that the Sun-Jupiter barycenter will be below the surface of the sun. But don't hold your breath.
Yeah, the sun doesn't have a hard surface, but I think maybe you can look at mass that is gravitationally, bound to the body. So you've got a coronosphere, which is
Yes.
is part of the sun because it's not going away. Anything that is expelled from the sun has been expelled. Any field that extends beyond it is a field, not the sun.
Yeah.
I mean, you could equally define the radius of a body as its Roche limit, the point within which objects may break up. So, of course, the Roche limit for the sun is quite a bit bigger than the sun.
Well, you could, but that wouldn't make any sense because
with the Earth.
Objects that would break up in the presence of an object are not part of the object.
It's to do with gravitational force rather than its, well, which obviously is dependent on its mass, rather than, a physical object.
I would still contend that if two bodies are, unless they are of absolutely equal mass, then the smaller one is orbiting the larger one, and it's not to do with the barycenter.
Well, even if one is 1.5 times the mass of the other, would you not regard that as a double planet?
Or as a double dwarf planet. I mean, it depends on other characteristics.
Another thing about the definition is the wording of that first criterion. A planet is a celestial body that is in orbit around the sun and is not itself a satellite of a planet. Sorry, of what? A planet. Yeah, but this is a definition of a planet. Yes. And you're referring to a planet.
Yes, it's a self-referential.
So effectively, you're saying it's an object which is in orbit around the sun and is not itself a body which is a celestial body in orbit around the sun. And it's a recursive definition, which I have expounded as a perfect example of the infinity of the universe. So I said, why didn't they just say, and is not itself a satellite of such a body? And that takes care of it. And I'm amazed that nobody at the IAU thought of that. It didn't take me long.
I suspect that this definition was drawn up rather quickly in order for there to be a date before the end of
the original team had been working on it for about 18 months. But others at the Congress thought that they could come up with something better in 4 days. So, as I say, teachers will tell you that if you rush your work, you're likely to get sloppy results.
Gary, just one last thing. Shall we take a vote? Who thinks Pluto is a planet? Raise your hand if you think Pluto is a planet.
Or use the reaction.
Reaction, yeah.
Yeah. Okay.
Yeah.
You buy the t-shirts.
Yes. So thank you, Jerry, for that.
No, and again, thank you, all of you, for being with us today. We've really appreciated it. Oh, I have one question, because somebody is still here from the Institute of Astronomy. If you unmute yourself, can you tell us who you are, please?
Oh. Yeah.
No response at the moment.
Okay.
Well, anyway, so
All right.
we didn't have everyone who registered for this actually here. We actually had 80, which was rather more than we had 3 weeks ago. So that's very welcome.
Yeah.
I will just say as a last announcement that our our FAS full-day conference was held this year at the Institute of Astronomy. Next year we're going to be in Cardiff. Tickets will probably be available from the beginning of January, so watch out for announcement in the newsletter, which Michael will send out to. If you don't see an FAS newsletter, then for goodness sake, have a go at your society committee and tell them they are meant to pass it on. There is no issue regarding GDPR, because we're not a commercial organization. You know, we're giving details of whether we think will be of interest to you.
Yeah. Paul, did you want to say something?
Yes, I just wanted to say that certainly over the. Sorry.
Oh, it's an echo.
Sorry.
Go.
We've got an echo somewhere.
Yeah. Okay. I just wanted to say that, I mean, since the time I was a president, during the time I was a president, the FAS newsletter has grown to be quite a substantial publication. A large part down to Michael, because he's done tremendous work in pulling contributors in and writing articles, and a lot of credit must go to Michael for the great work he's done on it. And if you've seen some of the older FAS newsletters, sorry, I've still got the echo. If you see some of the older FAS newsletters, the new one is significantly better than that. And if you're thinking of the old one, and I'm not sure I want to read it, don't. The new one is much better. Contact your secretary or treasurer, whoever receives it in your local organization. Make sure you get the newsletter and write articles and contribute. It's your newsletter after all.
Yeah, and can I just say as well that if you enjoyed tonight's presentation and you want to write about it, please do, and send it to me at newsletter@bedastro.org.uk.
Yeah. Right, well, once again, thank you all very much. Some familiar names there. Look out for the next newsletter and other activities.
Okay, so thank you everybody for joining us tonight. I'll bring this meeting to a close. So thanks very much. Hope to see you all soon.
Yep.